Hello everyone, Sayan this side. Today we are going to start off with the final week of our Quiz 1 syllabus in Stats 2, and you know it already, it's week 4. So, today what we are going to study is about continuous random variables, and more importantly, before that, we will be starting off with cumulative distribution function, okay, CDF. That's what we call it. So these are the two topics only that are present, and anything more related to these will be covered by the question session that I'll be taking up in the upcoming weeks. Okay, we are completing the syllabus well ahead before time, especially for your quiz one. So I believe that there is no problem if I take some question practice sessions and give you a good practice in that case. Okay, so let's start off and let's see what week 4 holds for us. The first topic, cumulative distribution function. Let's see what does it tell us. It says the cumulative distribution function CDF, as we denote it, of a random variable x is denoted as f of capital X as a function of small x is a function of the set of real numbers to 0 to 1 in the closed interval and is defined as fx of x equals probability x less than or equal to small x. A very complicated definition, but I would request you that you should not go by this definition. Let me explain it to you. What does it actually tell us? You see, f of x of small x. This is how it's represented. This is this denotation that I have done just now. Okay. So this is how the entire function is represented. And this says that it's probability that capital X less than or equal to small x. Now, what does this thing actually mean? You see, in the normal discrete cases, what did we do? Let's say I have got x, that means the capital X as my random variable, sorry, and it's taking the values 0, 1, 2, and 3. And it has got some probability since it's four variables. So for our since it's four values, so for our convenience, let's assume that each of them has a uniform distribution and it holds a value of 1 by 4 so that we can not get lost into the computation process of putting the correct values to get the entire PMF table sum as 1. Okay, so now what if someone would ask me that what is the probability that x is less than or equal to 2? What did we actually do? We said that I have to find the value of x which satisfies this equation or this inequality, I should say. It's not an equation, it's an inequality. So for this case, I know that x equals 0 satisfies this inequation. X equals 1, that satisfies this inequation. And x equals 2, that also satisfies this inequation. So these three values are the ones that satisfy this inequation. So how would I open it? I could say that for this equation to be satisfied or for this inequation, for this event to be satisfied, I can say that either either x can be 0 and there is a probability assigned to that, or x can be 1 and there is its corresponding probability assigned to it, or x can be 2 and there we have got its probability assigned to it. So when I used to sum the values up, why should I sum the values up? Because it's an either or case. Either x can take the value 0 that satisfies this equation, or x can take the value 1 that is satisfying this equation, this inequation. I'm always in the urge of saying equation, but it should be inequation. So please make a note of it. So either x equal to 0 or x equal to 1 or x equal to 2. This thing, this entire thing, this has an either or case that is being involved in it. Okay, so what should I do? I will just add these values. So what will be my value? It will be 3 by 4. And that is the exact job of my cumulative distribution functions. Sorry, my cumulative distribution function. So what does it actually do? If you can skip the formal definition for a moment, and if you can journey with me to the world of informal definition but a concept enriched definition, I can say the cumulative distribution function is the sum of all the probabilities assigned to it, assigned to each variable, sorry, assigned to each value of a random variable before it's um, assigned to each value of a random variable before its given value x, or I should say on or before its given value small x. Okay, and since we can change the value of x, that means in the previous example I could have taken the value of x to be 0, I could have taken the value of x to be 1, I could have taken the value of x to be 2, and I could have taken the value of x to be 3 as well. So I know that for that particular case or for that particular reason, my cumulative distribution function, it can also vary, and hence it's a function. But it's nothing, but it's only something that you already know, as I've told you. And if I write it in the summation format, okay, n is the uh, number or the specific value in which x lies. It is something like this. Okay. However, you do not have to remember this. You just remember the case that I had told you in the previous case, or in the previous definition, or this definition. It's more than enough for you to solve any question related to cumulative distribution function. Now, speaking of cumulative distribution function, each and every function we have seen that PMF has got some has got some property. Similarly, in the upcoming slides, you'll be seeing that PDF has got some property. So similarly, cumulative distribution function, it itself has got some properties. So let's uncover them. The first property, fx of b minus fx at a is equal to probability that a less than x less than or equal to b. What does this actually mean? You see, I cannot explain it to you with the help of a discrete random variable. I need a continuous random variable to explain this thing to you, and we'll be seeing this property in a very deeper manner when we reach the continuous random variable topic. So let's keep it on hold for a while. So let's go to the other properties. Second property, fx is a non-decreasing function taking non-negative values. How does this thing imply? You see, for each and every element, for each and every value, if I increase the value of x, as x increases, the particular designated value, as it goes on and on, as it goes increasing, my probability that too increases. How is that thing the case? You see, this is a continuous, a cumulative distribution function. We'll be seeing how to do this thing, although you know it. You see, x less than 0, it has got a probability 0. That means there is no probability of this function occurring. From 0 to 0 less than or equal to x less than 1, it has got a probability, not a probability, it's got a value. a value of 0.29. Similarly, as I increase the value of x to 4, the probability increases to 0.68. And as I increase the value to 8, it increases to 0.88. And as I go beyond 8, as we know that the sum of all the probabilities of a PMF table, they cannot be equal to, they cannot be more than 1. Sorry, not equal to. They cannot be more than 1. The maximum it can attain is 1. So this is what can we see from this case? It's either increasing, not either, it's both increasing, okay, and as I said, it is a, uh function that takes non-negative values, obviously, because probability can never be negative and we are summing up the probabilities. Okay, all right. Third, as x tends to minus infinity, fx tends to 0, and as x tends to infinity, fx tends to 1. Now, as x tends to minus infinity and as x tends to infinity, these are something that confuse the students very often. Okay, what is that thing? You see, I've got an x-axis in here. Here I've got minus infinity, here I've got infinity. And I've got a random variable capital X that can be traveled over its own axis, that can be traversed. Okay. So as x approaches negative infinity, what is actually happening? My random variable, the value of my random variable is actually decreasing. Okay. And since its value is decreasing, the chance that the function or the CDF will be there or a probability will be there, that's also decreasing. Okay. And since that decreases, ultimately at a point it will be 0. How? If we see this case, what is the range of the function? Although it's told to me that I have to find the range, so let me just find the range. In this manner we'll be solving a question by God's grace. So the range is this one. Okay, 0, then we have got 1, then we have got 4, and then finally we have got 8. So let's plot them right now in its axis. Okay, excuse me. So let's plot these functions. Okay, we had 4 values if I am not wrong. So it's 0, it's 1, it's 4, then it's 8. And what did the values tell me? 0.29, 0.68, 0.88, and 0.1. So when x is less than 0, it's 0 in here. When when x is between 0 and 1, it's 0.29 in here at this place. When x is in between 1 to 4, its value is 0.68. 0.68 in this place. And when x is between 4 and 8, its value is 0.88. Sorry, yeah, 0.88. And similarly, for this case, it's greater than 8. So it's 1 uh, as per the question. So can you see that as I am approaching towards positive infinity, after a particular interval or after a particular point, I'm getting the value to be 1. And as I'm approaching negative infinity, can you see that after a particular point, that is after 0, my probability is turning out to be 0. That's something that this property tells us. Okay, as simple as that. So let's move on to the next property. It says if fx rises from f1 to f2 at x1, then probability at x equals x1 is equal to f2 minus f1. This is something that we will be understanding more with the help of a question. So I should again tell you that we should keep it on hold. Okay. And then if fx of x x is continuous at x naught, then probability that x equals x naught is 0. Why? Because at a particular point, okay, I'll be having, what's the formal definition of probability? Something, some um, favorable condition divided by some total number of values or the total number of outcomes. Okay. So if fx is continuous, it takes infinitely many values at that interval, at a particular given interval. So it's just like saying that I'm dividing something, let's say x, or I should not say x, it's very frequently used, some a, some constant a divided by infinity, which I know it's always going to be 0. Okay. So small that we assume that it's 0. So that's something that we have discussed in here. Okay. I hope that these properties are clear to you people. And this question, this property number 4 and property number 1 are something that we will be seeing in our later slides. Okay. This is the question that we have already done. Sorry, again. So I don't think that you will have any doubt regarding it. This is a question that was based on the previous classes, on the previous lectures. Okay. All right. Now, this question explains the property number 4. Okay, let's see what the question asks us. It says the CDF of a discrete random variable x is given as fx at x equals 0 when x is less than 2, 0.15 when x is between -2 to -1, 0.35 when x is between -1 to 1, 0.75 when x is between 1 to 2, and 1 when x is greater than or equal to 2. Let y equals 2x squared plus 1. Find the PMF of y. Okay. So how should we solve this question? What should be our approach? Firstly, let's write down its entire PMF table once. Sorry, not PMF table, the CDF table, if I'm not wrong. I have it ready in front of me since I copied it from my notebook, so it's pretty obvious that I'll be having it ready in front of me. So fx at small x, that's equal to 0 when x is less than -2, 0.15 when x lies in this range, 0.35 when x lies in this range, 0.75 when x lies in this range, and 1 when x is greater than or equal to 2. Okay, so we are very familiar from the previous question that the range of this random variable the random variable x, that is tx, the range of that function, or the range of this random variable, that will be -2, -1, 1, and 2. Just see the less than or equal to sign, and after what value is that less than or equal to sign is present, that is a variable, that is a value that will be included in your range. A simple short trick. Okay, and now we are given a function y equal to 2x squared plus 1. So it's pretty evident that we have to convert the values. Okay, so when we have to convert the values, ty equals 2 into -2 squared plus 1, that's equal to 4 2s are 8 plus 1 9. For x equal to -2, and as well as for x equal to 2. Similarly, for x equal to -1 and 1, it is 3. Okay, so if I write it correspondingly, like if I write it as -2, -1, 1, 2, and ty equals 9, 3, 3, 9. Okay, all right. So for this case, I can see that 9 corresponds, the value of 9 in y, it corresponds to the value of minus 2 in x, and similarly the same case is for plus 2. For x equal to for y equal to 3, the value of x corresponds to 1, and for x equal to 3, it also corresponds to minus 1. So now I have to find the PMF of y. So I won't be wrong to tell you that P of y equal to 9 can be caused either when x equal to minus 2 or when x equal to plus 2. This is something that I hope that you know. And similarly, probability y equal to 3, that will be caused when x equal to, when x equal to minus 1 or x equal to 1. Okay. So now we have been given its we have been given its CDF, its cumulative distribution function. We are not given its so-called probability mass function that we can make something useful out of it. Had we been given the same thing, had we been given the PMF, then the same PMF would have been copied directly with some values to be manipulated. That we know, that we have studied in the previous classes, maybe in week 2, if I'm not wrong. But it's not something that we actually do. Excuse me. So for probability y equal to 3, x can either be minus 1 or x can either be plus 1. Okay. So for that case, what do we have to do? And here is the place where this property comes into use. Let's plot the values. Okay. Let's plot the values of x, 2, minus 1, comma 1. Okay. And here we have got 2. All right. So to find the probability at x equals minus 1, what do we have to do? You see, for finding out the probability at x equals minus 1, what if I take the CDF value from x equals minus 2 to x equals minus 1, and then I subtract it from the probability of, the CDF value of x equal to minus 1 to x equal to 1? Will I get the value of 1 to be only remaining, because all the other values, because the total thing for this case, you see, okay, just a minute, maybe I have gone a little too absurd in this case. Okay, so from minus 2 to 1, okay, from minus 2 to 1, I've got a value of 0.35 based on our previous definition, and from minus 2 to minus 1, I have got a value of 0.15. So remove if I remove this very place, if I remove this very place, yeah, this common place, will I be getting the value of minus 1 here? The answer is yes. Okay. But what about this particular range? What about minus 1 to 1? That is none of our concern, because we are dealing with the cumulative distribution function, and if we remove the cumulative distribution function of the previous range from the cumulative distribution function of this range, okay, for example, let me tell you something, like if I write it, okay, 0, 1, 2, 3, and here we have got the probabilities, so 1 by 4, 1 by 4, 1 by 4, and 1 by 4. And now I have to find, and what is the cumulative distribution function? So CDF for 0, that is 1 by 4. CDF for 1, that is 1 by 2. CDF for 2, that is 3 by 4. And CDF for 3, that is 1. And now I have to find the value of the probability at 2, let's say. Okay, so what should I do? for this case. I'll be just removing the probabilities from this part, right? I'll be just removing these very probabilities from the probability that I've assumed or the probability that I've accumulated till 2. Okay. So when I'll be removing these probabilities, what will I be remaining with? This part, right? 2. That's the same thing that I'm doing here. Okay. I'm not making up PMF tables because I don't know what the exact probabilities are. That's the main reason. Okay. So there's nothing to be worried about. So for that case, I can say probability at x equal to -1, sorry, probability at y equal to 3, sorry, probability at x equal to -1. Let's find it out for that case first. What will be my probability? 0.35 minus 0.15, that's 0.20. And similarly for probability x equal to +1, what will I be doing? I'll be doing something similar, but in a different range. Okay. I'm suffering with cold. And now when I have to remove the value from this case, I'll be doing something like this. 0.35, sorry, 0.75, because the entire value from 1 to 2, the CDF value is 0.75, and I'll be just removing the accumulative probability or the cumulative value that I have got before this place. So something like this. I'll be removing this thing. Okay. But if I mark it in the correct manner, yeah, I'll be removing this particular thing. So I'll be getting my value at 1. Okay. So for that case, what can I do? What can I write? For that case, I can write probability at x equal to +1 is equal to 0.75 minus 0.35, that is equal to 0.40. Okay. Similarly, for probability at x equal to -2, now it's oral for us. Why? Because we know that from this place I have to remove the probability before it. Okay, so 0.15 minus 0, that's 0.15. Okay, and for probability at x equal to 2, I have to remove uh, something before this place. So 1 minus all the cumulative probability before this. So 0.75, 0.75. So that's equal to 0.25. Okay, so the probability at x equal, so therefore the probability at y equal to 3, that is 0.60, and the probability at y equal to 9, if I'm not wrong, yes, that is equal to 0.40. Done. So this is my PMF of y, and if I have to make its PMF table, then it will be something like this: 3, and for this case it's 9. Yeah, okay, 0.60 and 0.40, and this is my answer. I hope that you have understood how to deal with this problem, and I hope that this makes your concept of the fourth property clear. That's what the fourth property has described, but it has been described in theory, and I have done it practically. Okay. Now, a very easy topic: continuous random variable. A random variable is said to be a continuous random variable if it takes infinitely many values in an interval. Okay, like for example, for my discrete case, I would have discrete values. Okay, I would have different values, and each and every value would be uh, something that won't be taken in an entire range. Okay, but for my continuous random variable, I can represent it in this manner. Okay, that means it takes all the values in between a and b. But for this case, if I remove the value of c for a better understanding, what would this do? this would only give me the values that were related. This would only take the value of either A or B, nothing in between. But for a continuous case, it would take the values of A, it would take the value of B, and the values of all the numbers that are included between these two ranges or these two values. So this is said to be continuous random variable, and we know that between two values in an interval, there are infinitely many number of values present. Okay, so that's something that this function or this property or this statement it says. Second, it has a probability distribution function. Yeah, for the case of discrete random variable, we had PMF, probability mass function. However, uh, sorry, just a minute. This is something. This should be density function. So sorry. Yeah, probability density function. So this is known as probability density function for the case of continuous random variable. That is denoted as f of small x and capital X. Capital X at the bottom. This is the case. The CDF of the continuous random variable is given by minus infinity to x fx of small x dx. Why is it so? We know it. Obviously, we know it. How? Uh, and that is integrated because that is the only case which we can use to sum up infinitely many number of values. Okay, so why this? Why uh, do we have to find out the CDF in this manner? From a value of minus infinity, and we don't know till what place is the value 0, the value of the CDF or the value of the PDF 0 to a particular value till which it becomes 0. That is absolutely 0. Okay. Plus from a value x1 to a value a, sorry, or to a value x, which can be varied fx at x dx, and it continues. We'll be understanding this case with the help of a question in the later slides, but for now you can remember it as a formula. And probability a less than or equal to x less than b equals integral of fx of small x dx. Now this is where we get the first property. You remember this property? Yeah, fx at b minus fx at a equals probability a less than or equal a less than x less than or equal to b. So now we'll be uncovering this thing. We know that for this case it will be nothing but probability, or if I break it, what will it be? Minus infinity to a uh, fx, or I should say minus infinity to b. That means all the values till the upper limit fx of small x dx minus a to, sorry, minus infinity to a fx of x dx. Why? This is minus infinity, this is plus infinity. Here we have two values a and b. So from minus infinity to b we have got some value, and from minus infinity to a we have got some value. So the common part, if I subtract this minus infinity to a from minus infinity to b, I'll be getting this part, and this is something that I have to integrate. Okay, so the total area under this region minus the total area under this region, that will be giving me the total area under this region. Why the total area? Because definite integral means the total area. Okay, all right, done. Okay, and if this thing is associated with this formula at the top, this formula, I can say that it's nothing but fx at b minus fx at a, because this is fx at x. I just substituted the values of b, where, sorry, the value of b where the value of x was present, and here I've substituted the value of a where the value of x was present. So this is the case. Hence, our first property in cumulative distribution function, that's also clear. Now, fifth one. This is a very important property, I should say. For deriving the PDF from a given CDF of a continuous random variable, the derivatives are usually sufficient. That means if a CDF is given to me for a continuous random variable, I'll be just doing its derivative. That means I'll be differentiating it with respect to the continuous random variable that will be given to me, and I will be getting its PDF at each and every point. And this is only for a continuous random variable. Mind it. Okay. So let's see how can we implement it with the help of a question. Okay, just a minute. Yeah. Okay. The probability density function of a continuous random variable is given as fx at small x equals x by 2 when 0 less than x less than or equal to 1, uh, half when 1 less than or equal to x less than or equal to 2, half into 3 minus x when 2 less than or equal to x less than or equal to 3, and 0 otherwise. Find its CDF, cumulative distribution function. Okay. So for x less than or equal to 0, what is my CDF? CDF, or I should say fx at 0. Let's use the notation that we just learned. Fx at 0. It's minus infinity to 0. 0 dx. Okay, that is equal to 0. Now for x less than or equal to, sorry, I just missed something in here. It will be x because this x can be varied. The top limit will always be x. Remember it in this manner. For x belonging to, for x belonging to 0 to 1, fx, how can we find out this thing? What we can do for this case is we can actually start off by putting the value of x as 0, and from that case it will be x till here. Okay, and what is it given us? 1 by 2 dx. So it will be half into x by 2 from 0 to x. So that is equal to half into uh, x by 2. So that is equal to x by 4 plus the previous integral, because we are finding out its CDF. So we have to include the uh, previous values as well in addition. Although it's 0, but we have to put the upper limit as 0, then 0 dx. So that will be equal to x by 4 only. Okay. Now for the next value, okay, that is for x being 1 to 2. For x belonging to 1 to 2, what do I have to do? Fx at x is equal to minus infinity to 0, 0 dx plus integral 0 to 1, because we'll be putting out the value of 1 after uh, the previous part is completed. Okay, so x by 2 dx plus integral of 1 to 2 half dx. So when we solve it, it will be x by 2 minus 1/4. Similarly, for 2, for x belonging to the closed interval 2 comma 3, fx at small x, that will be equal to minus infinity to 0, 0 dx plus 0 to 1 x by 2 dx plus 1 to 2 half dx. So okay, I've committed a mistake in here as well. it will be 1 to x, because the upper limit of the particular integral, that will be x always. Okay, and once we solve for the next interval that will be given to us, we'll be putting the value just as I have done right now. Okay, so for this case it will be 3 to x, and what is the function that's given to us? Half multiplied by 3 minus x dx. So on solving this, we'll be getting 3 by 2 x minus x squared by 4 plus, sorry, not plus, minus 5. And for the last case, since you see we are only given the value till 3, so any value after 3, that will be giving me a cumulative distribution function of 1, because by that point of time I would have added all the probabilities. Okay, so for x being greater than or equal to 3, f of x at small x equals 1. Okay, so if I were to write the thing, the answer in a formal manner, this would be 0 for x being less than 0, and then we have got, what should I say, uh, x squared by 4 for 0 less than or equal to x less than or equal to 1. Then we have got x by 2 minus 1/4 for 1 less than or equal to x less than or equal to 2. Then we have got 3 by 2 x minus x squared by 4 minus 5 for 2 less than or equal to x less than or equal to 3. And similarly, let me extend this thing, extend this curly bracket. Yeah, okay. So it's 1 for x being greater than or equal to 3. Okay, so this is my answer. Okay, now properties of probability density function, you know it. Any probability density function, this will be greater than or equal to 0. Each and every value that will be greater than or equal to 0 in any case. Okay, so this is something that we already know, since we are dealing with a probability, and fx, it gives us a probability in itself. Okay, pardon. Second one, the integral from minus infinity to infinity of f of x at x dx is equal to 1. Why? We are summing up all the probabilities and then we are getting the finalized value. Okay, and we know that when all the probabilities in a probability entry is summed up, be it discrete, be it continuous, it will always give us a value of 1. So for that case, this is the thing. And there are many other formulae. For expectation of x, we can write it as minus infinity to infinity x f of x dx. For variance of x, we know variance of x is equal to expectation of x squared minus expectation of x whole squared. So that will be minus infinity to infinity x squared f x dx minus integral of minus infinity to infinity x fx dx, that's whole squared. So these are the things that we can derive. We just have to replace probability by f and the so-called, what should I say, the capital X value by small x, and the summation, the sigma representation, with the help of integration. Done. There's nothing more than this. Okay, so I hope that you understood this thing. You understood this week's content. Yeah, it was very less, it was way too less than the previous weeks, but and it was the easiest, but it's the most important. Okay, and we'll be getting a better grip of the same when we practice some questions, which we'll be doing in the consecutive sessions. Okay, so thank you everyone, thank you for being till the very end. Thank you.